Alright, so what we'll do today is we'll just look at a few things from chapter 3. I think you'll need it for your assignment, your next assignment. If you look at, recall, two bodies problem. What is the two body problem statement? Or the expression
R double dot
right, R double dot plus
mu over R.
R cube R is equal to 0. Okay. And the solution to this is solution to two body problem is what? It's the Orphic equation or the trajectory equation, okay? Or Kepler's first law is the solution to two body problem. And if you look at the solution is what? It's R is equal to h square over mu over 1 plus E cosine theta. So here problem statement is expressed as a function of time. Okay. But solution is a function of normally theta. And always keeping in mind that the goal is
Sunday.
Hmm.
I see that how the solution is a function of the true anomaly, but how is the first one a function of time?
So what does that R double dot mean?
That is
Not time.
acceleration.
Yeah,
Yes.
that's not.
That's actually d over dt or d square over dt square of what?
Velocity over time.
R plus mu over RT cube. RT is equal to 0.
Okay.
So if you see here, you see why it is a function of time now?
Yes.
Because R itself is a function of time. R is varying as a function of time. When you take the derivative, you are trying to figure out how it is changing with respect to time. But here, this R is more of a function of theta. Okay? So here, what is the variable? The variable is actually theta. Okay? Now, although you can express this, see, this is also R of t, but at the same time, a square of mu 1 plus e cosine theta is a function of time. So we really need to know how theta is changing with respect to time to figure out how R is changing with respect to time. We cannot really understand, or we cannot really directly get an expression for how R is changing with respect to time. You understand? So to resolve this issue, all along our goal is to figure out R. R of t simply means I need to know where my orbiting body is at any given instant of time. Okay? And R is the position vector of the orbiting body from the center of Earth. And it could be position from the center of Earth, it could be position from some other, but we are always keen, or we always want to know what that R of t is. Okay? We introduce something called, keep in mind, we already know true anomaly. Anomaly is nothing but an angle. Okay? So we'll introduce something called eccentric anomaly. So how do we define eccentric anomaly? And this is defined for elliptical orbits. Or we look at it in the context of elliptical orbits. And we have, let's say, I would strongly recommend that you follow this first before you take notes. This will be a short question about figure out or just give me the true eccentric anomaly given the true anomaly. You have to It's a very simple thing, but you need to understand how to figure out central anomaly. Let's say this is your orbit. This is an elliptical orbit. For an elliptical orbit, where is the orbiting body? Huh?
Along that path.
Where is the central body?
On the focus.
Okay. This is where the central body is. Okay. It's always at the focus. Regardless of which orbit we are talking about, the central body is always at the focus.
You said what's always at the focus? Central body.
So what we do is, let's say we have an orbiting body situated here. So this is the periaxis direction or P direction. This is your true anomaly. Eccentric anomaly is again an angle. What we do is you guys are able to see this?
Yeah, sometimes because that's it.
Okay. So what we do is we circumscribe a circle to this ellipse. How do you circumscribe something? You know what circumscribe is? You know what circumscribe or inscribe is?
You draw a circle
Huh?
in there.
Huh?
You put a circle in there, like one side of the circle.
Right, but what is the difference between circumscribe and inscribe?
So like circle from outside, circle inside.
Right. So what you do is, if you want something to be circumscribed, this is the center, and you circumscribe. You use the compass, right? You've used a compass before. So what you do is, you keep the center of the compass here and you circumscribe with this as the radius. With the semi-major axis as the radius, you circumscribe. If you want to circumscribe here,
Yes, sir.
is that important?
Sort of, yeah. I'm paying attention.
If you want to circumscribe an ellipse, the radius is the semi-major axis. If you want to inscribe an ellipse, the radius is semi-minor axis. Get it?
Can you just show both?
So this is circumscribed.
Okay, I see.
Here you have circumscribed, right? Okay. So to circumscribe, what are you going to do? You're going to just take the center with your compass at the center of the ellipse. You're going to use the semi-major axis as a radius, and you are going to draw a circle, or you're going to circumscribe a circle. Okay? And what you're going to do is you're going to project this point onto the circle, onto the circumscribed circle. How do you project something? If you want to project this line, the projecting line has to be perpendicular to this line. Okay? Because this line can go this way, right? That is not projection. You have to make sure the projection is, this line is perpendicular to the base. And then, wherever this point, this line meets to the circle, you join this to the center, and this angle is the corresponding eccentric anomaly.
What line is that?
What line?
The purple line that you just drew? The one going to the center?
Projection.
So if that's the projection, what's the line that's perpendicular to the base?
This is the projection line.
Right.
This line, you join this point, wherever this point is the point where this projection intersects the circle. Okay? That intersection point, if you join that to the center, the angle this makes is called the eccentric anomaly. Okay? So here, theta is the true anomaly and E is the eccentric anomaly. Get it?
And inscribe would be inside of the.
Inscribe would be if you have, so what you do is, you use this as the radius and you'll draw this. So it won't touch this.
Can you draw the inscribe too?
I don't want to confuse.
So that's
So I'll tell you with, how do you inscribe a square?
Yes.
How do you inscribe a square? This is inscribing a square. Okay? So what is the radius of the square, or what is the diameter of this circle?
Half of it.
Huh?
Like half of it, like a regular radius.
The diameter of the circle is equal to the side.
Like
Circle. You cannot use words like that. You have to be. It cannot be the same as a circle. What do you mean by same as a circle? Same as a square. Does the square have a diameter? So what is it? What is E equal to? Same as the
diameter of the square, or the length of the square. The length of the side of one side of the square.
Okay.
Yeah.
So you cannot say diameter of the square same as the square. You have to be very precise. Now you get it. Marcus, side of the square, the length of the side of the square. Okay. So it is the length of the side of the square, right? Diameter of this circle. This is inscribe. How do you outscribe or circumscribe? Circumscribe is
This is the diagonal is
the diameter would now be the diagonal of the square.
what is it?
You see it?
Well, the circle that you just drew around it, that has nothing to do with the inscribe.
That is the circumscribe.
Right. The circumscribe is just the circle being inside the square. The inscribe is just a circle being inside the square.
Inscribe would be the diameter of an inscribed circle is the smallest distance between the sides.
Okay.
Circumscribe would be the largest distance. The diameter would be the largest distance. So what is the largest distance between the square? Inside, it's the distance between the two vertices of the diagonal.
So does this one not get written or drawn in a similar fashion as the one to the left?
So this is the diameter. The diameter is equal to the diagonal. So here, the diameter would be, if you circumscribe something, the diameter would be the larger side. If you inscribe something, the diameter would be the smaller side. Alex? Cell phone? Okay, can you keep it there? Okay.
One more time, the diameter of this one is what?
So this is inscribed. Sorry, yeah, inscribed. Get it?
That's the diameter of it.
The diameter would be the major axis, or radius would be semi-major axis. Semi-minor axis, sorry. Diameter would be minor axis. If you inscribe. If you
Okay.
circumscribe, the diameter would be major axis. Get it?
So the parallel line that we make has to go through the central body point that we had on the first explanation.
It's not parallel. It's perpendicular to the.
To perpendicular to the. I'm saying
Absolutely.
it has to go through what point? Because
Where the orbiting body is,
the orbiting body.
not the second one.
The diameter of that one is the semi-major axis?
Hmm?
Circumscribe?
Not semi-major, major axis. You should understand what semi-major and major. What is major axis and semi-major?
The major is the whole thing.
Yeah.
Semi-
So circumscribe is this is the diameter. The diameter is this, right, of the circle,
Okay.
or this. So both are. This is major axis. Okay. If you inscribe, what is the diameter? It is the minor axis,
Okay.
or the radius is semi-minor axis. Okay.
So,
Hmm?
because we just keep switching. So the diameter of this one is the major axis.
Yes.
The diameter of the other one is the minor axis.
Which other one?
Inscribe.
Right. So don't worry about inscribe right now. You don't have to. You should know what inscribe and circumscribe is. So if somebody asks you, you should be able to tell the difference. Okay? What we're trying to do here is we're trying to define eccentric anomaly, and that's the focus. So if you're asked to draw eccentric anomaly, or every true anomaly will have an eccentric anomaly. You realize that from this figure? As theta changes, your E also changes, right? So if you have your what is the true eccentric anomaly of this location? What is the true anomaly of this location? How do you depict the true anomaly of this location? Huh? First tell me the true anomaly.
The angle from the focus to that line.
The line joining. So you have this line, right? So you have, this is, let's say theta 1. What is the eccentric anomaly of this? So you do the projection first. Projection is you go from this line, draw a perpendicular to the apse line. Got it? And then what you do?
You project it onto the
You join. You join this line to the center.
And what is that represent?
Huh?
That represents the
Oh, sorry. You're right.
Yeah.
This is not the. It is this point, right? So this point is, this angle is E1.
So why do we have a true anomaly and an eccentric anomaly? See, I understand the true anomaly is going to tell us the angle from the perigee, right? And that's the true anomaly tells us the angle from the perigee. But the eccentric anomaly is basically telling us a projection of some circular orbit, but it's not going in the actual circle.
You have to keep in mind what I told you.
Okay.
So what this discussion was setting the platform for why we were introducing eccentric anomaly. So I'll tell you how this eccentric anomaly is used, but keep this in mind.
Okay.
R is a function of time. The solution we have is not a function of time. We are trying to get to an expression where we can directly correlate R as a function of time. So you have to understand something. Every parameter in our lives is a function of time. We are very comfortable knowing how something varies with respect to time. You do everything. All your groceries. You are always figuring out how your food is going to expire with respect to time. How you are going to grow with respect to time. Everything. How your engine is going to. How your gas is going to. So we are very comfortable with that notion of time. Okay. Although you may not see it mathematically, in real life, everything we are relating with respect to time. So when something relates not with respect to time, we get uncomfortable. You understand? Here it is, so you have to first understand how this theta is varying with respect to time. So you have to keep a track of what was the time when theta was, what does this position mean? If this orbiting body was here, what are you going to do? You're going to say theta, what is theta at this point? 0. And you're going to keep a track of what was the time at that point. Okay? And then you're going to figure out after a certain time how much has theta changed. Got it? And then you're going to say, with respect to that theta, what is my position? What is the position of the orbiting body? You understand theta is continuously changing, right, as a function of time. But you don't know how r is changing directly as a function of time. And that's what we are trying to get here. We are trying to get to an expression where we can directly correlate r with respect to time. You get it? And that is the reason we have introduced this eccentric anomaly. I'll get to how we use this eccentric anomaly. Okay? Just
Doesn't it have something to do with the center and the orbital body though? Doesn't it have something to do with the center point in the orbital body? So like he was saying that from the focus to the orbiting body is where we do the true anomaly. So the eccentric is just the same relationship between the center of this this orbit.
It's different. True anomaly is from focus to the orbiting body.
Right. And now
Eccentric anomaly is what?
the
From the center to the projection of the position of the orbiting body on the circumscribed circle. So it gets a little complicated, but if you understand what eccentric anomaly is, the concept of eccentric anomaly. See, if it's a circle, what is a property of circle with respect to orbits?
Everything.
it's the same homogeneous.
Radius is the same. That means that you can express this as a very simple function of time. See, your ellipse is changing the radius is changing, okay, for an ellipse. You cannot easily express that as a function of time, but for a circle, you can express that as a function of time because the velocity is the same, right? Because the radius is the same, the velocity is the same. It is a very simple function of time. Okay, you get it? We'll get to that. Just follow this discussion. Okay.
It's pitching background.
So what we do is we introduce something called mean motion. Right.
So your page that one.
This is 149. Okay. See, n is 2 pi over t. What would n be in terms of 2 pi over this capital T? So what is n? 2 pi is what? 2 pi is the angle, okay? And t is the orbit, the period, orbital period, okay? So what would n be in terms of just mathematics?
Would you say 2 pi was?
2 pi was angle, right? It's just complete one circle.
Probably rads per second.
Hmm?
Rads per second.
It's rad per second. So what is it? It's nothing but angular velocity. Okay? If you had you're covering 360 degrees angles in time period t. Okay? So here n is called mean motion. Got it? It's a very simple concept, but see, this is what makes orbital mechanics special. In the sense, you use general geometry, general terms, but you call them by a different name. Okay? So this is mean motion, and we introduce something called mean anomaly, which is n into t. And E is mean anomaly. Okay. I told you guys that anomaly is always an angle. Will this give you an angle?
Yes.
Rads per second times time. Yeah.
What is the difference between this time and this time?
Because that time is a period. T, capital T is a period, whereas small t is a section of time.
X is sectional time.
A sectional time.
Right. So capital T for this orbit would always be the same.
Okay.
This T would be See, for example, the mean anomaly for theta, what is the time t? It would be the time taken to go from this point to this point. The mean anomaly for theta 1 would be the time taken to go from this point to this point. So it will give you, this will also give you an angle. Mean anomaly will also give you an angle. Okay? And
So
this,
little t is changing with respect to true anomaly.
right, at a given point. So you're seeing three angles. One is true anomaly, another is eccentric anomaly, and then you have mean anomaly. Okay? So we'll do this. We'll name these V. This point is Q. This point is S. Okay, we have E, theta, and O. Would this distance, if I say this distance is A, the semi-major axis, would that make sense to you?
Yes, because it's the same all
It's the
around.
same distance as this distance, right? So this distance is A. From point OQ is A, where A is a semi-major axis, because O to this point is semi-major axis, right? And it's since this circumscribed circle, this is the same distance. Okay? Now what you want to see here is A cosine E is equal to AE plus Alright, let me do this. I'm not going to go through the derivation, and I'm not going to ask you to derive it either. I'll give you the expression. Okay? If you're interested, I can go to the derivation. The expression you need to know is, you may have to memorize this. Mean anomaly, the relationship between mean anomaly and true anomaly is E minus E sine or NT is equal to E minus E sine. And tangent E is equal to square root of 1 plus You want me to derive these equations for you? You sure?
Is it like,
It's not that difficult. Okay, let's do this. I'll do it in a special special class. Okay. So first, what I'll do is I think I'll give you. Let's look at something you were wondering, right? Why we were doing this, all this.
Yes.
Okay. So look at these and tell me, do you understand why we did it?
What is our little E in these equations?
Little e is eccentricity.
Oh, I thought it was something on the.
It's just eccentricity.
So look at that. Eccentricity and eccentric anomaly. So
Big E is eccentric anomaly,
Little e is eccentricity. Okay. So these are your two equations. Okay. Look at Kepler's equation. Now don't confuse this with Kepler's laws. Kepler's equation is different from Kepler's law. Okay. And the second one is Gauss's equation. So look at Kepler's equation and Gauss's equation and tell me if we have addressed this discussion. Think. Now this is what you are supposed to get out of this whole program. Think and tell me if I have.
well, you see NT, which is mean motion, or should I say mean anomaly?
Stare at it and tell me. Nobody?
So the mean anomaly is equal to the eccentric anomaly minus the like the magnitude of the angle. Like eccentricity is like the magnitude of the orbit, correct? Like, you know?
Eccentricity is the shape of the orbit.
Yeah, the shape of like to a certain magnitude, right? Or no?
Shape.
Just the shape.
So Gauss equation and
Alex, can you make sense what the earlier discussion was? Were you here for the earlier discussion, this part of the discussion?
I caught the back end of it.
Okay.
like, you want us to like,
See,
Like that
what I
now.
told you was, alright, so think about this. You have to really think and tell me. This is what you'll get paid for. The more you can think, the more you learn, okay? So this is I told you this is the two-body problem statement. The two-body problem statement is a function of time. However, when we solve for the two-body problem, the solution is a function of theta. And what I told you was, it is convenient if we figure out how to express this r as directly a function of time. So from that, can you justify this discussion and this rationale? No?
It's almost like
So think about it here, okay? You guys know the theta, right? Eccentricity is always a constant. What can you calculate? You can calculate E. If you can calculate E, you know the time. You see it?
you can calculate each of
If you know theta, you know E, right? Because eccentricity is known. Eccentricity is known. Small e is known. Okay? If you know theta, you can calculate E. This eccentric anomaly. If you know eccentric anomaly, you can calculate this time.
So how does that relate to this?
Now go the other way around. If I know the time, if I keep track of this time, I can simply figure out what E is. M is, how do you calculate N? You just figure out, you look at a position and then you figure out the time when that thing orbiting body comes at the same position. That would be 360 degrees. And you calculate, you know the time, you know this N. Okay? Got it?
Yes.
This is the time. This time is what? The time it's going to take from moving from one position to the other. And that's what we want to figure out. So if you know this time, if you're keeping a track, if you're just keeping a track of time, that's it, nothing. If we know the mean motion, you keep a track of time, you will know what this eccentric anomaly. At any time you know the eccentric anomaly. You get it? If you know the eccentric anomaly, you know theta. Right? If you know theta, you'll know R. Now,
So what?
see, this theta has to be measured every time.
In E.
To calculate R, to know this R, this theta has to be measured.
Okay. Theta.
Here you don't have to measure theta. If you keep a track of this time, T, theta is a function of what here? So here theta is a function of eccentric anomaly. Right? Eccentric anomaly is a function of what? Time. R is a function of what? Theta. So if you know time, you know R. When I say it's a function of, it's purely dependent on that quantity. That's what it means. You see it? A little bit? Alex?
I see a little bit.
Little bit? See, with this, you have to constantly measure this theta. You have to keep an instrument and figure out, okay, it is here, it is here. There is no way of keeping a track of theta as a function of time unless you use this. Here you can keep a track of this theta as a function of time, or R as directly a function of time. Okay? You get it? Little bit? How about you guys? Micah? Alright, so this is important because we'll finish with this. So again, consider this. Consider an orbiting body. Now, if you know the position, so this is the position R0, okay, and this is the velocity V0. What does this mean? This is just velocity at time t naught, and this is simply position r at time t naught. Got it? Given r at t naught and v at t naught, let's say you have, this is another position r at some time t, okay, and this is the velocity at some time t. Since orbital motion is restricted to a plane
What does it say after motion? Before motion is
restricted
motion.
to a plane see, this is purely based on geometry, okay? Can I express r in terms of r naught and v naught? Can I express r as a linear function of r naught and v naught? Right. So what you do is, just think about this. So this is the direction, right? So we have, let's do this first. So we have here. So just look at this. Okay. So what is this? This is F times R naught, and this is G times V naught. See this R, I can express this as some component of, it's like a triangle. This is sometimes G times V naught. See, this direction is the same as this direction. This direction is the same as this direction. Vector wise. Right? If you look at these two vectors, so it's actually, let's say this. This vector R is equal to this vector plus this vector. Parallelogram law, right? This is what? G times V naught. It's the same vector. It's the same direction. But it's multiplied by this G. We'll figure out what that G is. It is some constant. Okay? And this R naught is again just this R vector, R naught vector, the opposite, but it is multiplied by that f. Got it? So you can do the same thing with b. You can either do the same construction, or if you take the derivative of this, okay, f r naught plus g v naught. V would be, since r naught and v naught are established, they are constant, you will just get f naught or f dot r naught plus g dot v naught. This is because of geometry. Okay, if you apply this without taking into consideration orbital mechanics, it will still hold. If you just apply it for geometry, it will still hold.
It was still low.
Yeah, it will still be true. If you know the position, if you know two vectors in a plane, so this vector, what do you know? What do you mean? Do you know this? You know the magnitude of this, you know the direction of this. You know the magnitude of this, you know the direction of this. If you're trying to figure out the position and velocity at some other time instance, if you know how this f and g are changing with respect to time, you can figure out the position and velocity at that time instance. Okay? So we'll work this f and g. Here f and g can be expressed as Taylor series or can be expressed as a function of E, which is eccentric anomaly. Okay. So this is important for problem number 4.2. For 4.2, what you are being asked is, you're given R naught, you're actually given R, the magnitude, okay, at T naught, you're given RA, you're given declination, and you're given velocity at T naught. And you're required to find out R and V at some other after 30 minutes. Got it? So here you first need to calculate the vector R from this right ascension and declination. Okay? And then use that information. I'll give you expression for F G, F naught, G naught to calculate. So once you know R naught, B naught, if I give you an expression F and G, the expression will be in terms of R naught and B naught, or it will be in terms of eccentric anomaly. Okay. So now tell me, if it is 30 minutes, how do you relate that to eccentric anomaly?
If it's what?
30 minutes. It says, have you looked at problem number 4.2? Any one of you? Z has looked at it. We were discussing it yesterday. Anybody else? So after 30 minutes, see this, when it says 30 minutes, this T is at 30 minutes. Okay? So if you just substitute T in terms of seconds, you can calculate the corresponding eccentric anomaly. No? It's a homework problem.
When is homework due?
Friday.
Friday. Wait, when did we find out about this?
It was posted last Friday.
It's on Blackboard.
It's on Blackboard.
We don't have that session.